Good afternoon. Welcome to the latest installment of the ASPRS GeoByte series. This GeoByte, GRASS GIS, a point cloud evaluation resource, will be presented by Robert Zohr. Bob? Bob, are you ready?
Yes, I'm ready. Can I take it away then?
Yes, you can.
All right, perfect. Thank you, Ray. So I guess what we want to do today in this presentation is really address the purpose. I'm going to operate mostly off of this handout, and we'll scroll through that. But the purpose really is to demonstrate some practical point cloud strategies that we really find useful in evaluating vast quantities of point cloud data. So I'm with Bohannon Houston, and we're an engineering and spatial data company. We're located here in Albuquerque, New Mexico. And these are just some typical strategies that we use with GRASS, and I really hope that today's presentation will give you an idea of the power of GRASS and just how accessible it is for handling point cloud data. So this is the roadmap. I'm going to start off, and we'll do a little bit of introduction. We'll just kind of frame the problem set as I see it, and then we'll transition. After that, I primarily want to focus on just the data processing capabilities and show you just some of these applied workflows. For that, I've selected some data from Santa Fe County, primarily some LiDAR data, but we'll also look at some photogrammetry data. And then I'm hoping that once we've kind of churned through some data, that the conclusions or the takeaways, as I call them here, will be fairly evident, and you'll just see just how powerful GRASS GIS can be for dealing with point cloud data. All right, and then I think I've tried to gear the presentation to reserve some time for questions if anybody's got any burning questions out there. I'm not going to spend much time here on the abstract. I think that's in the announcement. You guys can check that out. Essentially, the main things I want to focus on are the kind of processing that we're doing with GRASS to really focus on data integrity and quality control. So essentially, we're looking at what do we have, what kind of LiDAR data or point cloud data are we dealing with, and what are the quality aspects of it. Primarily we'll look at things like spatial density, coverage, regularity, and then we'll also kind of take a look at some of the elevation qualities as well. We'll do that interactively, and I think you'll be surprised, but we'll use essentially one tool out of GRASS. It's the import tool called r.in.lidar. It's extremely powerful, and then we'll also pair that up a little bit with some other GRASS tools and some other FOSS4G tools on the analytical side to give you a flavor of how you can do some more with integration. All right. So moving into the kind of the framing, I put the links to the GRASS website here. You can learn a whole lot more about GRASS there. And then, as you probably noticed, I'm on a Mac, and so this is location for downloading the GRASS binaries for the Mac. But you can also use it on Linux systems or Windows as well. So I kind of frame this here as, okay, point cloud data. If you've worked with point cloud data, I think you probably understand it can be a big data problem. We're getting vast quantities, and then luckily for us, I think we've got nice open source solutions out there that help us address that challenge. So on the one hand here, I've outlined a couple of the challenges as I see it. The volume on these files, typically if you receive LiDAR data, you're probably talking about millions of points per file. On a project scale, that can easily approach billions of points, and so the volume is definitely an issue. And then how we visualize those big volumes of data, I think can be tough. GRASS has a lot of tools that help us with that challenge. And then, the resolution is, I think, another challenge that is going to compound those volume and visualization challenges, because we're getting new LiDAR sensors out on the market that are just producing more dense data than we've ever seen. And then, we're starting to see a lot from image source, where we're getting point cloud data sets that are developed off of images that just really compound those two volume and visualization challenges. On the advantages side with GRASS, for us, it's really, getting in the raster domain. That speeds things up tremendously. I think you'll notice that as we do the exercises. We also have a lot of read options. So LiDAR point cloud data often comes with a whole host of attributes, and GRASS gives us an ability to parse all that information out in many, many different ways. And then the last advantage here, and I think there's others that we could put on the list, but we really like being able to read in single files. We do that very often. But then GRASS also gives you an ability to bring in a whole listing of files, and I'll show you how that works too. And that's nice. You really almost have the ability with GRASS to treat LiDAR point cloud sets in a file structure almost like a VRT format, if you're familiar with GDAL virtual file formats. So a lot of advantages with GRASS. The next graphic here that I put together, this is for I did this for a talk last fall up in Denver, and really was just trying to put a schematic together of how we approach projects and use GRASS in our workflows. And it all starts with these piles of LiDAR tiles or point cloud data sets. We're trying to import that. We use, as I mentioned, r.in.lidar primarily for that purpose. But GRASS in general, you can import all kinds of geospatial data sets, and a lot of that is working through the GDAL libraries. Once you get the data in, for us it's all about analyzing it and visualizing it. Like I said, we're primarily dedicated in the raster domain, but you've got a whole, GRASS is a fully functional GIS suite, and so you can do vector processing, image analysis, just a wide range of tasks. Once you do the analysis, you want to look at the data. GRASS gives you some capabilities there, and then we often take the visualizations outside of GRASS with some other tools that I've kind of graphically posted there. Scripting is huge in this kind of workflow. We're often just reading a big bucket, and we do that mostly with bash scripting, but you can also do a lot on the Python side if you're so inclined. And then for us, we also are trying to take the data that we're visualizing out of GRASS, and so again through GDAL and some other functionality, GRASS is pretty robust on the export side, so you can move that to other GISs if you need to. I put an integration bubble here too. We'll do a little bit. There's more integration happening every day with GRASS, and I know that the community is working on more integration with tools like PDAL, and so I think the frontier is really exciting on the integration front. All right, so that's kind of the framing of the topic. Now we're just going to start to look at some data itself. Like I mentioned, we put together 9 LiDAR tiles from Santa Fe County, and I put together this little view of where we're going to be working. This is going to be Santa Fe proper that we'll be looking at. That's just north of where I'm at here in Albuquerque within the state of New Mexico, so pretty centrally located within New Mexico. The 9 tiles themselves cover the downtown area. of Santa Fe and then up into the foothills. So I tried to get a little bit of relief there. And then this is just north of the Interstate Highway I-25. All right, so that's just some context of where we'll be working. And you know, when you have a lot of LiDAR data, you may not really know a whole lot about it. So one of the first things you need to do is understand, you know, what kind of format do I have. This first exercise that we'll do, I'm going to make sure we're in our directory here where my LiDAR is housed. I'm just going to do that here in the terminal. You can see I've got a number of LAS files. I've got the 9 files here. And on my GRASS install, we are only going to be reading in LAS 1.2. Well, this data happens to be LAS 1.4. So this is a PDAL info command that I'm looking at the metadata on one of these LAS files and then piping that over to search for the term minor to give me the minor version. It says 4. So off the bat, I know I've got to do some prep work, and I'll show you what we do to translate that over to version 1.2 so we can bring it into my GRASS workspace. But the next thing that's important for GRASS from a metadata perspective is knowing spatially, okay, what coordinate system am I working with. So I'm going to take that same PDAL info command here, except this time we're going to look for the reference term, all right? And so this is taking the data out of the header. You can see we've got spatial reference. If you're not familiar with this, you know, there's EPSG codes embedded in here. That's how we're going to set up our GRASS workspace. But if you want to confirm what an EPSG code is, you can always just copy this first little bit or some of the text here in your output, which is what I've done here next. We're in New Mexico Central Harn, so I just took that bit of text. You can Google on that, and you can see, hey, I got the first hit here is out of spatialreference.org, and it gives me more information about the coordinate system, including the EPSG code. And so that's what I'm going to really rely on to set up our GRASS workspace. All right. So now that I know something about the data, we would next convert the LAS 1.4 data into 1.2 format. I'm going to save you guys the trouble of doing that. I've already done that, but essentially put on the screen here, made another directory called 1.2, LAS 1.2, and then I just am running another PDAL translate command in this case where I'm getting a directory listing of all the LAS files, and then I'm writing them out to version 2 in this case, and then the output writes those files into that directory, and then when this command executes, I've got all my LAS files. So those will be the LAS files that we'll read, and at this point, now that kind of got some understanding of the data, I'm ready to start up GRASS. So I'm going to be running GRASS 7.3 today, and you'll notice we've got terminal window starting up, and I'm going to work off of my desktop. I don't have anything in I made a little folder called GRASS here. There's nothing in there. It's looking for something, and so we're going to just start with a new GRASS location. It's going to ask me for a name on that. I'm going to call this GRASS Live. Okay. And then you've got some different methods. You could bring in projection and datum terms from a georeference file. We do that sometimes. But I'm just going to use the default simple method here since we went through the work of establishing what our EPSG code is on this. I'll use that and say next. You got a little search window here that comes up. I can type in my 2903. That's for our New Mexico Central Harn. We'll say next. We've got a datum option. I'll OK that. And then we get a little summary of what we're setting up for our location. I'll just finish that. Now it says, do you want to create the default region extents and the resolution at this point? I'm going to say no. We'll talk a little bit more about region later. And then it's asking me, do I want a map set with my username? I'll say I'll cancel that. We'll just work on the permanent GRASS map set. All right. So now I'm ready to start up my GRASS session. You notice that our terminal changed to a regular GRASS terminal with the welcome screen. And then I've got a couple of other windows that come up. I've got my map display window, and I've got my layer manager. So this is going to be where we put a lot of our map data, and then over in the display is where we'll see our results, okay? And then in a terminal, that's where we can issue commands, but you could also issue commands here. There's a console in the layer manager that you could type in commands there and get the different modules to come up. All right, so back to the handout. At this point, we've got our GRASS setup going. I'm going to change directories in the terminal to where our last 2 data lives. All right, and then the next thing I say here is let's run some r.in.lidar. Let's import our LiDAR data. So I'll do that, and then I'll let that run in the background so we can type other things there. Any of the commands that you see here that are GRASS commands, we could run them through the graphical user interface here, which is popped up for r.in.lidar, but you could also run them simply as commands. For this one, we'll just kind of walk through from left to right what we'll plan on doing. I'll scroll a little bit down here. The first thing I've got here is I want to do a directory listing, because there's a couple of options. I mentioned you could bring in a single file, or you could bring in a list of your files. Right now I don't have a listing in this directory, so we'll just paste that command in here, and we'll make a point cloud list file, and we can look at the contents of that. And you can see it's just a simple text file now that has all the 9 1.2 files, and we're ready to go with that. So instead of an import las file, I'm going to give it this point cloud list file that I created. And you notice as I start to populate this, we're going to extend our region. The region concept's important in GRASS. That's our analysis window of how many columns and rows are we dealing with. So I'm going to use the LiDAR information to extend the GRASS region or analysis window. And then I'm also going to set this flag to set that region to be the current computational region within my GRASS session. You notice we don't have anything in this data set or in this GRASS workspace because we just started it. So in my command that is kind of below here on the handout, I'm going to call this intensity. The first thing we're going to do is going to bring in the intensity data. And that'll kind of give us a picture of what we're dealing with these data sets. You can define the raster resolution. Essentially, we're going to be using this program. It's a binning approach to bringing in the point cloud data into a raster form. So you can specify an output raster resolution. Our data is in feet, so I'm going to do 4 feet. Then the next tab over, you've got the statistic. Well, how do we want to bin that? In this case, I'm going to leave that as the mean. That's the default, but you can see this is where a lot of the power comes in to GRASS and r.in.lidar. You've got all kinds of statistical measures that you could use to bin the data. I'm going to leave the other options here on this tab. You could do some trimming. I'm going to leave those blank at this point. You could also do some subtraction. This is also powerful using a base raster to subtract the point cloud values. I'm going to leave that as is. Then next you've got a selection tab. That's where you can do a lot of filtering of the data. So maybe you only want to bring in a particular Z range, or we're going to bring in intensity. We could filter by intensity range. Then you can also change whether you want to bring in the first return, last return, whatever, and classification. So yeah, in this initial example, we won't do anything. And then lastly, you got some optional tabs. I'm going to check a couple of options here. Since I've already defined our projection, I'm just going to say, hey, we're going to work in the projection we established. We're going to bring in, this is important for the intensity, we need to flag the eye. And as you notice here at the bottom, we start to build out the GRASS command. That's the actual command that I've got listed in the handout. So that's very convenient for us. And then if we want to copy that, we can just click the copy, and then you can paste that contents of the clipboard into your GRASS terminal window to execute the command. And the last one I'm going to do is allow to overwrite the file. So at this point, I think the command is about what I've got on the handout. So we'll try it out here and click run. And you can see it's starting to cycle through the tiles now. And I'll move that over. And what we'll be doing now is we'll be reading all of those 9 tiles. It's going to create an intensity image for us, and we'll get a posting, and that's kind of what I have here. It'll tell us when the program's complete that we've got about 148 million points that were read in off of those 9 files. And then it'll also give us a timestamp. We'll see what it does here for us at this point. So it read them in. That's the 148 million. Took about 39 seconds in this case. So roughly 150 million points in 30 or so seconds. I think that's what's really impressive to me about GRASS. So I'm done with that. Now we can go check it out in the map window. So here's my intensity that we just created. And you notice it looks, maybe if you're familiar with intensity, a little strange. This is a default color table. We can change that here with the context menu. I can set the color table. It knows I want to set that one. So I'm going to give it a gray color table with an equalization. So we'll run that. And there we go. There's our first exercise to kind of see what do we have in the way of these data. All right. We're not going to stop there. Now we're going to start to take the data out. So this is 16-bit scaled intensity imagery here within GRASS. And I'm going to output this to just a graphical format here. So this is going to be a PNG. I created an output folder here just on my desktop. You can see that command, the r.out.png, just created our PNG file. So now we've got a nice graphic. You can put this in a document, and it's another nice visual. But that may not be the best thing if you're a geospatial hack. So the next thing I'll do is I got a little GDAL command here. This is GDAL translate. And this will assign the 2903 coordinate system to the PNG, and it'll output a geotiff for us. Okay, so we go back. Now we've got a geotiff here in our output folder, and if you wanted to look at that in your desktop GIS, you could do that, and that's what we're loading up here, that geotiff in QGIS. And there you go. So now we've got our LiDAR visualization here in QGIS, and we can integrate any other kind of data that we wanted to. A lot of times what we like to do is process that data out to KMZ. So this is just another GDAL command, takes the data, makes a Google Earth KMZ for us. And there it's done. So we can launch Google Earth on this, and here we go. And this is what I like to call passing the Google test. It just gives us kind of an independent check, maybe some verification that we've set up our GRASS workspace correctly and that our coordinate system and our LiDAR data is at least in a reasonable, independently checked correct location. All right, so now that we know a little bit about our data, what it looks like, I'm going to start to do the spatial statistics. And the first test we'll do to assess these data is a distribution and regularity test. If you're familiar with the base specification from USGS, you can check out more details on this kind of test on page 5 of this specification. And this, our GRASS really lends itself to this kind of test because the test really says, hey, put together a density grid and assess what percentage of the cells in your grid have at least one point in them from a regularity and distribution standpoint. For this kind of QL2 level data, it prescribes doing it at 4.66 feet. We'll leave it at 4 foot in this exercise. And it's always a good idea to check that you're in the same location, which I think I am. And then we're going to run the same command, reading the same point cloud data, but with a little bit of modification. So we're keeping the resolution the same, but this time we're going to apply a return filter. So the base LiDAR spec says to only look at the first returns, so that's what we'll do. We're going to change the method. So instead of the mean value, we're using the N method, which is really a count method. So it's just going to count the number of returns per 4 foot by 4 foot cell. And then you can see that now we've got a reduced amount of points because we're only looking at the first return points. We've got 96 million instead of the initial 148 million points. All right. So, but what I really am after is how many points have 0, or how many cells have 0 points in them. So that's what we're going to do next. But I'll just kind of show you first. Now we've got this other data set. It's called the count first map. And you can kind of make out we've got flight line patterns, different collection patterns that are visible. And so this is pretty interesting just from seeing not only how the data is collected, but what we'll do next is, all right, where might we have some coverage issues or some regularity issues? For that, I'm going to run a different GRASS command. This is map algebra. The command's called r.mapcalc. So it's basically a logical type analysis where we're going to assess in that first map that we brought in of the counts, if there's a 0 in the data set or a cell with 0 data, let's make that no data or null. Otherwise, let's just let the initial map come through. So created that now, and that's called the null map. That's what I have pictured down here in the graphic. All right, so I can just show you. Here's the null map. So this map, and you may say, well, okay, we displayed that, but we don't see any changes. Well, that's because underneath that, I still have displayed the first count map. So when I turn that off, now it may be hard to see. We've got a few black pixels that are popping through that are no data now from our MapCalc analysis that don't have any points in those cells. Okay, so the next thing that I've got here is we're going to compute statistics on that map to understand, okay, what percentage of data might not have any points within this raster. So this is the GRASS r.univar. It's a statistics calculating program. I've done something where I've parsed away the equal sign and replaced it with a comma, and then I output that to a CSV. So if we look at our output folder, now I've got a CSV. We can bring that up in Excel or your favorite spreadsheet. Essentially, this is the output of that command, which is really what I have in the handout here of the table. So the next thing that when we want to understand what percentage have at least one cell or 1 point within the cell, we just calculate the number of cells within the region, divide that into the number of cells that actually have data, which are the first two highlighted cells. That gives me, I added this at the bottom, that we've got 99.97% of this AOI have at least 1 point. You kind of got that now too off the range. We've got the min, the max. There's other statistical information like the mean number of points per cell, 6.87 in this case. And then we've got a sum too. This tells you exactly the same information that we already knew, how many points were read in within our region. All right. So that's good, but we might want to really assess, well, where are these 0 cell points? So I'm going to paste in this region command. That just helps me confirm what our columns and rows are, what we're working in. And now I'm going to create an inverse mask with map calc. So we're going to take those null pixels that have 0 points in them. I'm going to make a binary map with this other logic statement. And so this will just be no data pixels will become 1, and then everything else will be no data. So next I'm going to aggregate those with the grass r.clump command. And you notice, man, I've got more than 2,000 clumps out there that might have no points in them. Well, I don't necessarily want to look at all those, so there's an add-on, and you can always install different add-ons with the g.extension command. This is called r.area, and we'll run that, and this is going to filter out any aggregate with less than three cells. Okay, so that reduces the data volume a little bit in this case. Then I'm going to turn that into a vector. All right, and I've got 634 polygons that were made. I'm going to add a little bit of information. We're going to add a column here in GRASS to that vector data set, and I'm going to then upload how many acres might I have in those 634 in each of those polygons. So that's what we've executed next. And then I'm going to, again, just for convenience, take all that analysis and write it out to KML, and we'll take a look at that too. But I'll just show you, we can add that vector file. I called it count first null mask, for lack of a better term. We can add that. Now you can see a little bit more visibly where those null data cells happen to be. We can look at the attribute table. You can see I've got my acres. The largest one is 0.03 acres. So these are pretty small, but they may warrant some inspection. So this is really a convenient way to get at that data. If I go back here, you can also see we've output our KML of that. So there's the same information just in Google Earth. And one thing you notice, some of these are no points were recorded over the swimming pool here. This is the Santa Fe Hilton, and we've captured that swimming pool, but we've also got some occlusions. There's some other pools here. And then we can kind of look at maybe there's some flight pattern issues, maybe the speed of the aircraft. So it gives us an idea of, where might we have some issues that we want to inspect or understand further. All right, so moving along, one of the things that a lot of people ask is, I've got this LiDAR data, how many points per square meter do I have in this data set? GRASS is great for that. This is the same command we've been running all along. Although you notice now, since we're dealing in feet in our GRASS database, I changed the resolution to the r.in.lidar command to reflect kind of a 1 meter equivalent. So now we can run statistics on the count map. I didn't change the method. We're leaving that as count. But I've got a new name for this. I called it count 1 meter. Everything else is pretty well the same. I did set the region of analysis to reflect this 1 meter. And so now that's finished. We can go take a look at that map. So I'll add the count 1 meter map. And then what I did in the handout is I just got a histogram on that count map. So you can see the shape of the curve there. And then we can look at the statistics on that map. And this tells us essentially the same information we got off of r.univar, except we're reading in the data at a different resolution. We're back to the 148 million points within the region, and it gives me a nice quick mean. So the average cell here has 7.1 points per square meter, since that's the resolution of a raster map. So this is really convenient to get a quick common, and you could adopt that if you just want to bring in the swath data by itself and check out the density calculus on that kind of data set as well. So up to this point, we've kind of assessed the data, looked at some different analyses, but we really haven't looked at elevation. That's what we're going to start to do next. All right. So make sure I'm in the same GRASS region or directory location. And here I'm going to look at the point classification information on one of these. So again, I'm running a PDAL info command here. We're looking at the statistics, and I'm asking PDAL to analyze the classification and give me the values, enumerate the values of the classification in that file. You see I've got a 1 or no ground, or not ground. I've got a 2 for ground, which we've classified some ignore break line. I've got 17 for bridges, and then I've got 18, which is a high noise. So the next thing I'm going to do when we bring in the elevation data, I'm going to ignore the high noise. So now this looks a little complicated. We'll explain what we're doing here. But what I have done is I took all of those GRASS commands and I made a little bash script here. So I'm going to fire that off, and so it looks like it's cooking. So while that's running, I'll come back here. On the elevation side, we're going to make some traditional digital surface models here, but we're going to do a couple of different modifications. We're going to run the r.in.lidar command. You notice I'm going to change the resolution. I'm going to bring it down. This data is dense enough that we could really get a 2-foot view of the data. So we'll change that primarily. I already mentioned that we'll bring in the data with filtering by classification. And then I'm going to also change it up a little, and we'll look at first return. This first r.in.lidar command is going to be a traditional kind of what's the canopy. So on my method, I changed that up to read the max point within the 2-foot cell and get the max elevation off of the data set from only the first returns. And then the subsequent commands for r.in.lidar, we're keeping resolution the same, but we're going to change the method to minimum on the next two. The classification filter remains the same, but I'm going to read in a minimum data set of first returns, and as well as a last return only data set. And so that'll produce some, I think, pretty interesting effects that we'll show you. Because we're bringing in the data, you already saw at a 4-foot, we've got a few holes. If you bring the data in at a 2-foot resolution, you're going to have a whole lot more holes. There's a lot of null filling strategies or no data filling strategies you can employ in GRASS. There's actually a command called RDOT fill nulls. That takes a little bit of time to run, so just a real quick and dirty null filling strategy. We can grow the results of these imports out by 1 pixel, and that's what I'm doing here with the RDOT grow command. I've got the defaults where we're bringing in that first return, min, max, and last return. We're growing them out by a pixel, and that'll really fill in a lot of the gaps that we might have between scan lines and that sort of thing. Once we've filled in the data, you can see sort of the result of that here on the handout. In map A, I've got a elevation map that is filled in, and it's you know, fairly good coverage at this point, even just using the RDOT grow command. Map B is the minimum, but bringing in the first returns. You can see that's also got a good coverage. And then map C is the last return data. Also, we've grown that out, but you notice that there's a lot of holes. So what we're seeing there is where we may not have a last return, and primarily you can kind of make out the road network and things like that that really just don't have a last return, and so it's reflected as a null data set. Next, what we're going to do, I'm not going to really do anything with the max data. We're going to really focus on the min data in this elevation exercise, and I'm going to patch together map C, and then anywhere where there's a hole, I'm going to bring in map B, which is the first return data, and so we'll get a complete minimum data set with that merging using the RDOT patch command. And then once we've done that, we'll run shaded relief maps so that we can kind of, and that's through RDOT relief, and we'll just get a visual on what that data looks like. So that's what I have here on the handout. You can see that on the left-hand side, it's pretty, you know, heavily dominated by canopy, and then you got a lot more terrain information coming through on the right-hand side. Looks like our script's still running, but we can go here and check it out. I already have a few results, so we'll just take a look. Here's the minimum first return data set. And what's interesting about this is, you know, here's just using very simplistic methods out of the box, but you are sort of removing a lot of the vegetation. Obviously not everything with the last return, but you get a real feel and a sense for what's going on here terrain-wise, that this you know, traditional canopy level look at the data just is masking. So you can see we're, you know, looking at the Santa Fe River corridor, a lot of vegetation in through there, and so in the traditional mode of a canopy level surface model, you've got a lot of obstruction, and then looking through with the minimum data set, you really kind of take a lot of that away, and you still are you know, dealing with the surface model, so you've got buildings left in there, but you really stripped away a lot of vegetation. All right, so go back to the handout here. Now that we've looked at that kind of data, the last thing I want to look at with you is just some photogrammetric data. I mentioned that we're getting very big point cloud data sets from imagery. I'm going to kind of skip ahead here, and we'll fire off another shell script on this one. We'll let GRASS cook on that while I come back and we explain a little bit more. Oops, I need to make sure I'm in the directory where that lives. And then we can, I'll just bring that up and run that again, make sure that that's cooking. I think it will at this point. So I'm going to just give you a quick visual on what this photogrammetric point cloud looks like. Here's just a view again of that Santa Fe Hilton. We've got the swimming pool there. This is data set that's made off of a process called semi-global matching, and it's photogrammetrically based, so you can kind of get a sense of, we're looking at a one stereo model view here in my display. This one stereo model, all the other LiDAR that we looked at, the 9 tiles, is about 150 million points combined. This one stereo model, which is derived off of a 6-inch acquisition data set, is 150 million points essentially in this one stereo model. We're looking at an RGB data set encoded with false color IR, and so what's nice is as these data sets start to proliferate, you could bring them in and look at those RGB qualities. That's what we'll do here in this next exercise. I'm not sure that r.in.lidar, at least my version, doesn't bring in the RGB natively, but what I've done here is I've issued a couple of PDAL translate commands to basically translate the different RGB values into the intensity, which GRASS does bring in, as we've seen. And so we could bring in a raster image that is strictly read off of the point cloud data and their inherent RGB values. So in this case, I'm issuing the blue to intensity, but you could do the red and the infrared as well. Then what we're doing is we're doing everything what we've done before. We're going to look at the elevation on this photogrammetric point cloud. I'm keeping the resolution at 2, so it's the same. And then one of the things that we look at a lot is, okay, what are the spatial extents of this point cloud? I know there's a lot of tools out there. We could extract a boundary. You can even do that with PDAL. But GRASS is nice, if you brought in something as a raster data set, you can essentially turn that into a polygon and vectorize it. So it's some of the same things we were doing with the node data cells, except here we're looking at all of the data cells, and then I'm running a clean command that removes any small polygon less than a certain threshold in size, and so we get rid of a lot of small occlusions and things like that with that kind of processing. And then these last commands here are just r.in.lidar, bringing in the intensity values that we ferried into separate bands. And so we'll make an RGB image strictly off of the point cloud with that. And then next we kind of see the results of that analysis. This is elevation brought in from the photogrammetric data with the polygon boundary around it. I've got a shaded relief that we've made that we can compare to the other data sets. And then, like I said, this is also an image derived strictly off of the point cloud RGB values that have been brought over through GRASS via intensity. So that script finished up, and I also incidentally made some output in Google Earth, so we can kind of compare. There's our DSM converted over to shaded relief, and this gives us just a quick sense, and we can compare that to what we've got here on the LiDAR data set. And I'd say this is a real advantage, as you start to accumulate all these different variables out there, then you can do change detection analysis off of the elevation, find buildings that may not have been there when you did your LiDAR collect versus when you got the image collect, and so becomes very powerful tools. So that's the surface model. I mentioned that we were doing a footprint polygon. This gives us that indication of that stereo boundary. So if we were reading a large bucket of data, we can quickly assess, okay, what's our footprint coverage with this kind of polygon analysis. And then the last thing that I've got here is this is an image that is coming into GRASS as a point cloud and then back out. You've got some of the occlusions and whatnot, but certainly if you've got overlapping models, some of those get filled in, and then you could fill the rust with interpolation or and potentially use some of GRASS's image processing commands strictly from a point cloud source. So that's the photogrammetry side. Kind of the last thing to mention here is what we do on a project scale is we scale up this processing, so we script huge amounts of data. I've got an example here. This is over the city of Lubbock, and we've processed an intensity image also with GRASS. This is just bringing in that data and then combining it with the DSM, so you sort of get a little bit of a 3D look in this intensity. And here we are over Texas Tech University. And then that pretty much does it for the presentation. I just want to conclude here. Hopefully it gives you an idea of just how powerful GRASS and its brethren in the open source community are for processing. We really probably couldn't get our jobs done as effectively as we do today without the open source software community. So I've listed here the GRASS team. Got to thank them, Michael Barton, who produces the Mac binaries. But then we do a lot and get a lot of benefit out of PDAL with Howard Butler and his group, as well as GDAL. And then in case you were wondering, that point cloud viewer is out of UC Davis. It's called the LiDAR viewer. That's a really nice tool. On the data side, got to thank Santa Fe County for their support, as well as City of Lubbock, and then our aerial acquisition partner on these projects is Aerographics. And then I'll scroll back here to my contact information. If you've got any questions, I think we still might have some time for questions, and I'll leave my contact up there in case anybody wants to jot that down and send me an email later. So Zan, I don't know if we want to field any questions at this point.
Wonderful, Robert. Thank you so much. The first question we have is, how can attendees receive a copy of your handout? Is it available for download?
It's not available for download at this point, but if you want to email me, we can certainly make arrangements. This handout is pretty huge, so we'll have to figure out what we do, but they can email me.
Fantastic. The next question is, does the initial file conversion from last version 1.4 to last version 1.2 cause any loss of resolution in the data or other changes?
No, not that I'm aware of. I mean, it's pretty straightforward command. It's really just changing the format. Now, you've got to be careful about if it depends on the intensity values in that translation remained as 16-bit. So if you want to do some scaling, you might have to get a little more fancy with your data. But in this case, if you're asking about the intensity data in particular, those values remained at 16-bit. There could be some other aspects that we're not really bringing in, maybe scan angle that might get truncated from the resolution, but or from that conversion to 1.2. But in terms of what we're analyzing, there's no real loss of data.
And are you familiar with any changes with the classes that are over 31 for version 1.4 when it goes to 1.2? What happens to those additional classes?
In terms of their changes?
Correct. If they happen to be reclassed to something else, for instance, the BABI classes of 40, 41, or 42.
Oh, yeah. Those, yeah, you might have to pay more attention to that if you want to analyze some specifics there and figure out how to handle those mappings. in this case, this is pretty simplistic, so we're not experiencing much change there.
Okay, and what is the plan with GRASS for R.I and .LiDAR and PDAL?
Well, my understanding is there's development for more integration out there. In fact, I think right before I got on, I saw some communication on the PDAL listserv, and the discussion was that the integration had been a little bit stalled, but it sounded like it was poised to get picked up again and move forward. So I would expect to see some news on that front in the near future.
Great. And finally, are there any GRASS GIS communities or support sites you would recommend for new users?
The primary site that I would recommend, and you can get a whole lot of information, is the main GRASS site. So we'll go back to that here just for your reference. So it's grass at os.osgeo.org, and so there's a lot on getting involved, development, I mean, you name it. So this is, I would say, your one-stop shop for the software. The download, it'll recognize what operating system you're on, and you can go from there. And then I know the GRASS community is always looking for people to get involved in development, so this is where I would recommend people go.
Fantastic. That was all the questions we've received so far. Thank you so much for presenting today. It was a great GeoBite session.
All right. Well, thank you very much, Sam.
I think we're concluded, Ray.
And thank you everyone for attending. This GeoBite has been recorded and will be available on the ASPRS website in a couple days. Have a good weekend.
All right.